All right, so here we've got a firework that's launched straight up, and shortly before it explodes, it's 10 kilograms and moving upwards at 20 meters per second. And then it explodes over the course of 0.1 seconds. Now we've got a 3 kilogram piece that we can see moving 15 meters per second at a 45-degree angle above horizontal, and a 2 kilogram piece that's moving 30 meters per second straight to the horizontal direction. And the largest piece, a 5 kilogram piece that maybe our detectors have lost track of. Maybe we've got a radar that can only keep track of 2 objects at once. So this is moving in some unknown direction at some unknown speed. And let's say we want to figure out what's going on here, or what happens during this period of time. So let's try to figure this out. And I think probably the best way to do this, to organize the information, is to set up a momentum chart. So we're going to be investigating initial momentum, change in momentum, and final momentum as the columns. And what rows should we include in this diagram? We want to keep track of the momentum of what?
One for each of the pieces?
Yeah, one for each of the pieces. Because even though at the beginning they're all bundled together into one lump, we know that that one lump is going to explode into 3 pieces. We don't want to start with an initial value of one value and then split it into 3 values. We want to keep track of 3 values the whole time. So just like if you have 2 objects colliding and sticking together, they were 2 objects to start with. So even after they stick together, you still want to treat them as 2 objects. They just happen to be moving together. Same idea here, but in reverse. We know that this one object is going to split into 3 objects. So we're going to treat it as 3 objects from the start. Like if you imagine that this was sort of pre-split into 3 pieces. And of course, it's not necessarily split yet. Maybe it really is one whole object. But the fact that we know it's going to split into 3 pieces means we should be treating it as those 3 pieces from the start. So we're going to treat this as object A, object B, object C, and of course, we'll want a row for total momentum as well. So these are what we need to keep track of. And I'm probably going to regret not having very much vertical space, so I might want to modify that a bit. Yeah, something like that. Okay, so let's see what we can fill in. For example, we know I think we can figure out the initial values and at least some of the final values. For instance, how would we find the initial momentum of object A, the 5 kilogram piece? How would we calculate momentum of this piece here? Yeah, we can take, well, it's not the entire original firework though, because our object A is not the entire firework. Object A is just this piece of the firework. So how do we calculate momentum typically? We want to multiply what times what? Yeah, we take 5 kilograms because object A is 5 kilograms. And we multiply just those 5 kilograms times the 20 meters per second upwards. So that will give us 5 times 20, that's 100 kilogram meters per second. And since everything is in kilogram meters per second, I'm just going to write that off to the side as a reminder and not bother writing kilogram meters per second every time. And what about object B? That's 3 kilograms moving upwards at 20 meters per second. So what would that be? Yeah, 60. And object C was 2 kilograms times 20 meters per second. So that gives us 40 kilogram meters per second upwards. And then we can add those together. Can we just add the values here? Can we just add 100 plus 60 plus 40? In this case, yeah. And why is that? Why can't we just add the magnitudes rather than needing to split them up into components? Right, they're all in the same direction. Since these are all in the same direction, they're all pointing straight up, then we can just add them together. In fact, geometrically, we add them head to tail. We've got 100 plus 60 more in the same direction plus 40 more in the same direction. That adds up to 100 plus 60 plus 40, 200 in the upwards direction. So the initial momentum is 200 straight up. And it's probably a good idea to write these out in components anyway, because later on they are going to be moving in different directions. So let's fill these components in as well. These all are moving just straight up. So they've got no x component, and their magnitude is their y component because it's straight up. So 0, 100, 0, 60, 0, 40, and 0, 200. Any questions on the initial values so far? And I think we can fill in some of the final values because we have some of the final velocities. Object A, we can't really yet. I mean, object A, we could at least write out 5 kilograms times this unknown V final. We don't know what V final is. It's some unknown vector, specifically V final of object A. But we can at least write its momentum in terms of that unknown. We could even fill in the components. We could say it's 5 V final X, 5 V final Y, even though we don't know what those components are. For B and C, though, we know those values. C, for instance, is just 30 meters per second to the east or to the right. I guess this is up and down. So let's say we've got up, down, east, and west. This is a reference point. So 2 kilogram object times 30 meters per second. So that'll just be 60. We don't have a little bit of that one. So 60 due east. So what would that look like in terms of components? Yeah, 60, 0. And likewise for B, we know it's 15 meters per second times 3 kilograms. So that'll be 3 times 15 will be 45 up and to the right. And that we're going to want to split into x and y components. So how would we do that? If it's at a 45-degree angle, how do you split that into x and y components? What's the multiplier there? Yeah, we can just use cosine and sine of 45. Although we want to multiply that by the magnitude, because the magnitude here is 45. So we multiply 45 times cosine 45 degrees. In other words, 45 kilogram meters per second times cosine 45 degrees, and 45 kilogram meters per second times sine of 45 degrees. So that'll give us the x and y components. Those will both be positive because it's to the east and up. So that'll be, let's see what that is. Because since we're going to want to, and in a lot of cases, I would leave these as like just 45 cosine 45 degrees or something like that, or write it as √2/2. But since we're going to be adding these up, I think it's a good idea to have decimal approximations. So 45 times sine 45 is 31.8. I'm just going to round that off to, well, let's be accurate, 31.8. And then sine 45 and cosine 45 are the same because it's an isosceles triangle. So the y component is also 31.8. So we've got the x and y components of final momentum of B and final momentum of C. Is there anything else we can fill in here? Total final momentum. And what do we know about that? What should we usually assume about the final total momentum? It should equal to the initial total momentum under what circumstances? When can we assume that? Right, if there's no outside force, no force from something else. We got to be careful about that here, though. In a situation where you're launching a firework upwards, what force would you expect to be acting on that firework? Yeah, we might have gravity. In fact, we should expect gravity, and there might be wind also. Let's assume for the moment that there's no wind. Let's assume that there's just gravity. So gravity we're going to take as Earth normal. So we'll assume that during this process, there is a force of gravity. Force of gravity. And we can treat this, we don't really need to worry about the forces on the individual objects yet. We can just look at the total force of gravity on the whole system. So treating this as one big object, what's the mass of this one big object? Yeah, 10 kilograms. And what's the force, how would we find the force of gravity on that? How do you calculate how strong the force of gravity is? Yeah, we can use 10 meters per second squared for G, because generally force of gravity is mass of the object times acceleration of gravity, which we should also really treat as a vector here, a downwards vector. So that's 10 kilograms times, do you want to use 10 meters per second squared or the more accurate 9.8 meters per second squared here? I mean, we're already using a calculator, so we may as well use the more accurate version. So we've got 10 kilograms for the whole object times 9.8 meters per second squared. So that'll be 98 newtons. So that's the external force. There is a downwards external force of 98 newtons. And that's the total external force on the whole system. And you can actually get this either by looking at the whole object, just take 10 kilograms times 9.8 meters per second squared, or by looking at each object individually. If you take 5 kilograms times 9.8 plus 3 times 9.8 plus 2 times 9.8, the total external force on all these objects is still 98 newtons. So 98 newtons downwards is the total force on the system. Total external force, I should say. Because there's also internal forces between the objects, but that doesn't matter for a change in total momentum. But generally, if there is an external force, change in total momentum is not going to be zero. It's going to be what? How would we calculate that? How would you figure out how much the total momentum changes as a result of this force? Yeah, if we multiply the force on the system times the change in time. This is the idea of impulse. The total impulse acting on the system from somewhere else, specifically from the planet, is the force exerted by the planet on the whole system, which is the force of gravity, 98 newtons downwards, times the change in time. So if we multiply those, 98 newtons times the amount of time it takes, we're talking about 0.1 seconds later. 98 times a tenth of a second would be 9.8. So that'll be 9.8 kilogram meters per second. Because newtons is kilogram meters over seconds times seconds. multiply by seconds, and that cancels out one of the seconds. We're left with just kilogram meters over seconds. Any other questions on that change in momentum so far?
If we did take into account something like friction, would we just, how would we figure out the delta P then?
Do you mean like air resistance?
Yeah.
If there was air resistance, that would presumably be a force in the downwards direction, because air resistance is just the opposite of the direction of motion. So if an object's moving upwards, it experiences air resistance downwards. And we'd have to know how strong that force of air resistance is. Air resistance force depends mostly on the speed of the object, the cross-sectional area, because that determines how much air it has to push out of the way, and also the density of the air, because that determines how much mass of air it has to push out of the way. If I remember correctly, I think it works out to something like speed squared times cross-sectional area times density of the air, possibly with some other proportionality constant. But presumably that would be given, because if the speed is changing, then the air resistance force is also going to be changing. So I would assume that if there is an air resistance force, either that would be given, or you'd have enough information with everything else that you could solve for it as the last unknown. But in this case, let's assume that there's no air resistance. Let's assume that the firework is compact enough, streamlined enough, and not really moving all that fast. 20 meters per second isn't all that fast. So let's assume that air resistance is not a significant force here. Also, if there was wind would presumably be a partly sideways force, because I wouldn't expect the wind to be pushing straight up or straight down. It would be pushing either to the right or left, or maybe on some diagonal. I think in the homework problem you mentioned, there's enough information that you can find the total initial momentum and the total final momentum, and then investigate what's the difference. So if you know all the initial values and all the final values, you can find both totals and then take the difference. Then go back to the idea that the total change in momentum equals force times time. Divide by time, and you know the total force acting on the system from outside. In this case, though, we don't know the final velocity of object A, but we do know the change in momentum, 9.8, and that's 9.8 in which direction? Yeah, straight down. So we can write that as just 0, 9.8. Or negative 9.8, 0, negative 9.8. And that's pretty small compared to the size involved. We've got a 200 kilogram meters per second upwards total momentum. We're changing it by a downwards quantity of about 10. So we'll end up with 190.2. In fact, we could just add those up. 0, 200 plus the change 0, negative 9.8 is 0, 190.2. So we know the final total. It's upwards and almost as large as the initial total. And now what's the only unknown left? Yeah, we still don't know V final of object A, but we can now figure that out because we know that these three quantities have to add up to 0, 190.2. So let's try setting that up as an equation. We know this vector plus this vector plus this vector equals this vector. And since we have them split into components, we can write this out in terms of one component at a time. So looking at just the x components, we've got this unknown 5 times v final x plus 31.8 plus 60, and those have to add up to 0. So that's an equation we can solve for v final x. And then if we take a look at the y components, we've got v final, or 5 times v final y plus 31.8 plus 0, and those have to add up to 190.2. So we now have two equations we can solve for the two unknowns, v final x and v final y. In fact, we don't even really need to mess around with any system of equations sorcery because these are just in terms of one variable. These are already separate. we've got one equation with just v final x as the unknown, and one equation with just v final y as the only unknown. So combine like terms, we get 91.8, and I'm going to subtract the 91.8 from both sides, and then divide by 5, and that'll be 40, no, 20, less than 20, 19 something, 18 something, 91.8, divided by 5, 18.36. So that's the final x component of the velocity of object A. And then likewise for y component, we can subtract 31.8 from both sides. And you get 158.4. And then divide that by 5. So v final in the y direction is 31.68. So that now tells us the final velocity of object A. We now know it's got a negative x component, a positive y component. So let's fill that in. We've got negative 18.36, positive 31.68. So it should be something like that. And we can even fill in the rest of the momentum chart now. If we just take those x component and y component and multiply both of them by 5 kilograms, that gives us the final x component of A's momentum and the final y component of A's momentum. And then with all these values, we can subtract to figure out the change in momentum of each one. Final minus initial equals change. Any other questions on that so far? And then if we wanted to, we could also, for instance, find how fast it's going. Like if we wanted to find the magnitude of the velocity, the actual speed, how would we find that magnitude now that we know the components? Yeah, Pythagorean theorem as usual. We take x component squared, ignoring the negative because the negative is going to go away when you square it anyway. X component squared plus y component squared, and then take the square root. That'll tell you the actual speed, the magnitude of the velocity vector. And then also if you wanted to find the direction, like let's say you wanted to find this angle, the angle it makes with horizontal, how would you find that angle? If we know the sides, we've got 18.36. And if we're just treating these as sides of a right triangle, I'd ignore the negatives, 18.36 and 31.68. Yeah, we could use the tangent idea because tangent of this angle equals opposite side over adjacent side. So you can take opposite over adjacent, 31.68 over 18.36, take the inverse tangent, and that'll tell you the acute angle inside this triangle. So you could say it's that many degrees above west, or that many degrees up from west. Any other questions on that? And by the way, if you did subtract, like let's say we actually subtract these. Let's say we take a look at object C, and you could do the rest as well, but let's take a look at object C specifically. If we just subtract final minus initial, we've got, for instance, 60 minus 0, 0 minus 40. So the change in momentum for object C is 60 to the right, or 60 to the east and 40 down. What could you use that for? Why would that be useful? Or what else could you figure out from that change in momentum? What causes a change in momentum? Yeah, a force. And I wouldn't necessarily say an external force in this case, because C is experiencing an external force from gravity, but it's also experiencing forces from what other objects? What else is pushing on object C here? Because gravity didn't make object C veer off to the right. Gravity is just pulling straight down. Yeah, the other pieces. Objects A and B are pushing off from object C. The reason object C is able to shoot off to the right is because it's interacting with the other objects, as well as gravity. So what you could do is you could take this force, or this change in momentum, 60, -40, set it equal to force times time, F times delta T, the whole idea of impulse again. We know the amount of time this explosion takes is 1/10 of a second. So you could divide both sides by 1/10 of a second and find the total force acting on object C. And that's not any one specific force. It's just the total force acting on object C as a result of the explosion, the push off from the other objects, and also gravity as well. So if you wanted to find the force that the explosion itself exerts on object C, you could solve for total force on object C and then subtract the force of gravity on object C. Because the total force on object C is a combination of gravity plus the force of the other pieces from the explosion. Because the explosion here is basically the three objects interacting with each other. These three pieces pushing off of each other during the explosion. Also, if you wanted to figure out if this counted as elastic or inelastic, what would you do? What do we mean by elastic versus inelastic? Yeah, we look at the velocities, and it's not just about the momentum though, because momentum being conserved is about whether there's an external force or not. But yeah, kinetic energy is really what you want to look at. Momentum being conserved just means this is a closed system in terms of the forces, which it isn't in this case. But elastic versus inelastic is all about kinetic energy. You take a look at the total kinetic energy of the whole system before the interaction and the total kinetic energy of the whole system after. And you could use the usual formula, kinetic energy equals 1/2 times mass times velocity squared. So at the beginning, you take 1/2 times the mass, 10 kilograms, times the velocity, 20 meters per second, squared, to find the initial kinetic energy of the whole system. Afterwards, the pieces are moving separately, so you have to treat them separately. So 1/2 times 5 kilograms times this speed squared, and you can ignore direction, just look at the magnitude of speed squared, because kinetic energy is directionless. Plus 1/2 times 3 kilograms times this speed squared, plus 1/2 times 2 kilograms times this speed squared. That'll tell you the total final kinetic energy, and then you compare. If they're the same, then it would be an elastic interaction. And I don't think they'd be the same here, because we've got a lot of stuff going on. If you end up with less kinetic energy than you started with, then that's inelastic. Some of the kinetic energy has turned into other things. It hasn't disappeared. Energy doesn't just vanish. But the kinetic energy in an inelastic collision, some of the kinetic energy turns into other forms, usually leaving the system as heat. Maybe the objects get warmer. In this case, though, I'm guessing, if I've set it up right, I'm guessing that you'll end up with more kinetic energy at the end than you started with at the beginning. So we would sometimes call that a hyperelastic or superelastic collision, if you end up with more kinetic energy than you started with. And how could that be possible? How could a system have more kinetic energy afterwards than it started with? Where does that extra energy come from? How could the system gain kinetic energy? Yeah, from the explosion itself. Although probably that's not euthermal. What's presumably causing the explosion to happen? How do you make a firework explode? What energy is stored in the firework before it explodes? Yeah, it's got chemical energy, right? This object is presumably packed with a small explosive charge, which has high amount of chemical energy. It's an unstable compound. When you light it, it explodes, turning the chemical energy into kinetic energy and thermal energy. So the extra kinetic energy presumably comes from some of the chemical energy that was stored in the explosive charge in the first place. So I would call this hyperelastic or superelastic. I think it varies depending on the textbook. But it's gaining kinetic energy because other forms of energy that were already stored inside turn into kinetic energy. You can generally see this happening in systems where the interaction releases energy that was already stored in the system. Maybe like in this case, you've got a small explosive charge that has chemical energy turning into kinetic energy. Or what's another way that energy might be stored in the system to begin with? What's another form of energy that can be stored up? Is there some other way you could squeeze a bunch of work into a small space and then release it later? Yeah, pressure of a gas would be one way to do it. If you have a container full of some gas and you push the piston in really far, so you get very pressurized gas and then lock it in place, then later you unlock it and the piston shoots back out again as the pressures equilibrate. So you could store energy in a pressurized gas. Electrical could also do it. If you have energy stored in a battery or a capacitor, well, I guess a battery is technically chemical energy turning into electrical energy. But let's say you charge up a capacitor and then you hook the capacitor up to a motor. The capacitor discharges, powering the motor, which turns it into kinetic energy. So that would be stored electrical energy in the capacitor, turning into kinetic energy by powering the motor. Another simple mechanical example would be a spring. If you take a spring and compress it, you're doing work to store potential energy in the spring, lock it in place, install it in some mechanism, and then release it later. And that energy, the stored potential energy, turns back into kinetic energy. Maybe you've got a spring-loaded cart and the carts collide. During the collision, the spring is released and they push off at a faster speed than they started at. So they gain kinetic energy in a hyperelastic collision because the potential energy that was already stored in the spring becomes kinetic energy. The total energy of the system doesn't change. We're just turning some non-kinetic energy into kinetic energy, or vice versa in an inelastic collision. Any other questions on the collisions or explosions? All right, let's take a look at torque and how it ties into angular momentum. And I think it's going to help here to look into how this relates to the translational motion stuff we've already seen. If we compare translational motion to rotational motion. For example, if we take a look at the idea of impulse. In impulse, this idea we've been working with is that the change in momentum is equal to the force on the object times the change in time. Or to put it another way, if you solve for force, force is the rate of change in momentum. The force, specifically the total force on the object. The total or net force on the object tells you how fast momentum is changing as time passes. If we can set up something very similar for rotational motion, what's the rotational version of force? Right, we've got torque. And of course, there may be several torques acting on the object. So let's say the net torque, the total of all the torques acting on the object. And time is just time, regardless of whether you're talking about translational or rotational motion. So net torque times time is very similar to the idea of net force times time. It's the amount of, I guess you might say the amount of effort that you're putting into the object times how much time that effort lasts. So if force times time equals change in translational momentum, then torque times time should equal change in a new quantity called angular momentum or rotational momentum, which we usually write as a capital L. And the terms angular and rotational are used kind of interchangeably here. You might see this referred to as angular momentum or rotational momentum. It means the same thing. Likewise, this you might see referred to as translational momentum or sometimes linear momentum. That doesn't have to mean the object is moving in a straight line. It might be moving in a curving path, but it's still moving in a linear fashion rather than moving in an angular fashion. The important difference is translational motion means the object's position in space is changing. Rotational motion means the object's orientation is changing. And you could measure those in terms of how far it travels as a distance versus how much it rotates as an angle. Any questions on the difference there so far? So you apply a force to an object for some amount of time and you change its translational momentum. You apply a torque to an object for some amount of time and you change its angular momentum. And to investigate what those really are, going back to the idea of translational momentum, how do we define translational momentum in the first place? That's just what times what? Yeah, mass times velocity. Or since there's a change here, that'll be change in mass times velocity. And since the mass of the object presumably doesn't change, we usually pull out that mass and write it as mass times change in velocity, because a constant multiplier can be pulled out of a delta. And let's take a quick look at the units there. If we investigate the units of measurement, what is mass measured in? So we've got kilograms, and velocity measured in, yeah, meters per second. So that's our usual kilogram meters per second for the units of momentum. What about force? What's force measured in? Yeah, force is measured in newtons, capital N. Usually if a unit is named after somebody, the unit gets capitalized, or the abbreviation gets capitalized, but the name does not. So newtons written out in full, lowercase n, newtons as a unit, capital N. And then time as usual measured in seconds. So do these units match up? Does newtons times seconds give you kilogram meters per second? What is a newton anyway? Those should match up, right? What's another important formula? Yeah, that's kilogram meters per second squared, right? And if you forget that, you can always go back to the idea that force is mass times acceleration. Probably the most important equation in the study of motion. Force, newtons, mass, kilograms, acceleration, meters per second squared. So newtons has to be kilograms times meters per second squared in order to make this work. Kilogram meters per second squared multiplied by an extra seconds. One of the seconds cancels out, canceling out the squared here. So you just get kilogram meters per second. So these match up. The units all work. If we try constructing something similar for torque, so far, how have we been calculating the magnitude of torque? What's our usual formula for that? What do you multiply together to find out how much torque is being used? Yeah, distance from the pivot times the force, and also times sine of the angle between them. But the sine of the angle between them doesn't contribute any units. Sine, cosine, and tangent are all unitless quantities. So we get radius, which is measured in meters, force, which is measured in newtons, and sine theta is unitless. So torque is measured in Newton meters. And you may remember from 7a, newtons times meters is technically joules, because that's a force times a distance, so that's work. But we usually don't abbreviate this as joules. We just leave it as newtons times meters, because torque is not an energy. Torque is a force applied some distance from the center, some distance from the pivot point. So we usually don't abbreviate this as joules. We just leave it as newtons times meters because we want to emphasize that it is not an energy, it is a torque. But that's the units of measurement for torque, newtons times meters. If we multiply that by time, we also get times seconds. And let's see if we can investigate what angular momentum is. Because angular momentum is going to have to be newtons times meters times seconds If we combine those together, newtons, as usual, is kilogram meters per second squared. But we're multiplying that by an extra meters and also multiplying by an extra seconds. So the meters are going to combine. One of the seconds cancels out. And we're left with kilogram meters squared over seconds. Is that the same units of measurement as translational momentum? No, these are not the same thing. Translational momentum, kilogram meters per second. Angular momentum, kilogram meters squared per second. The fact that they have different units means they are fundamentally different types of quantities. We call them both momentum, and they act the same in a lot of ways, but they are not interchangeable. You can't just turn translational momentum into rotational momentum, at least not directly, because they are not the same thing. As opposed to, for instance, if you're looking at translational kinetic energy and rotational kinetic energy, they're all measured in joules. They're all just types of energy. So translational kinetic energy and rotational kinetic energy are somewhat interchangeable. They're both the same energy. They're just different kinds of energy. But translational momentum and rotational momentum are fundamentally different units of measurement. So you can't, for instance, just add them together. You've got to treat them separately. Also, if we try to split this up, translational momentum splits up into mass times translational velocity. But what does angular momentum split up into? Can we write that as just a mass times a velocity? If we try that, let's say we put in mass. We don't want to use translational velocity though. We'd want to use rotational velocity, omega. Omega, the rotational velocity representing how fast the object is spinning. And what is rotational velocity measured in? What's the units of measurement for how fast an object is spinning? Radians is the angle, but angular velocity is how fast it's spinning. So that's angle per second. So this is radians per second. The radians is technically unitless. When we say an angle's measure is like pi over 2 radians, that's really just pi over 2 in radian measure. Radians is not technically a unit. Radians is a unitless quantity. So angular velocity, we usually read it as radians per second, but it's technically just 1 over seconds. And then mass would be in kilograms. So kilograms times 1 over seconds, does that give us the correct units of measurement? No, we are missing something. So mass alone is not enough here. Angular momentum is not just mass times angular velocity. Yeah, we're going to introduce this new quantity, the moment of inertia. Moment of inertia, usually written as a capital I, is basically the rotational version of mass, in the sense that mass of the object is how difficult it is to translationally accelerate it. Like if you want to make the object get faster or slower or change direction, mass is how difficult it is to do that. More mass means you need more force to get the same acceleration. Moment of inertia is the rotational version of that. Mass is how difficult it is to change the translational velocity. Moment of inertia is how difficult it is to change the rotational velocity. And the units for that, in order to get this side of the equation to match up with the kilogram meters squared per second, what are the units of angular momentum, or sorry, moment of inertia? What are the units of I have to be to make this work? What units are missing if we want to make this look like this? Yeah, we need kilogram meters squared. We've got the 1 over seconds just fine. We just need kilograms times meters squared. So moment of inertia is a quantity that represents how difficult it is to change the rotation, and it's got to be measured in kilogram meters squared. And we can use this to build a simple formula for it, at least one example of a formula. Kilograms is a measure of mass. Meters is a measurement of distance. And what's the most important distance involved in any rotational situation? If you've got some sort of rotating object, what distance do we usually care about? Yeah, the radius, the distance from the pivot point. So the basic formula for moment of inertia is the mass times the radius squared. However, this only works if all the mass is that distance from the center. So for example, if you've got, let's say, a long but lightweight stick and a heavy mass at the end of it, and you're swinging that around, all the mass, or almost all the mass, is that one distance from the pivot point. So you can treat that as just the mass of that object at the end times the distance from the pivot point squared. Or if you've got like a bicycle wheel, most of the mass is on that outer rim. Very little of the mass is in the spokes. So you can take the mass of the bicycle wheel times the radius squared, and that'll tell you the moment of inertia of that bicycle wheel. But in other cases, it's not as simple as just mass times radius squared. It's always going to end up as kilogram meter squared as the units, but it's going to be a more complicated formula, typically some fraction times a mass times some distance squared. But generally, moment of inertia describes not only the mass of the object, but also how the mass is distributed. Is all the mass at the outer edge? Is most of the mass near the center? Is it more spread out? Is it shaped like a ball or a cylinder or a disc or a rod? The shape of the object, how the mass is distributed, matters quite a bit. So moment of inertia is not just the mass of the object, it's the mass and how it's distributed from the pivot point. Any other questions on that so far? All right, so in general, keep in mind that mass is how difficult it is to change the translational velocity, and moment of inertia is how difficult it is to change the rotational velocity, how difficult it is to change the way an object is spinning. So keep that in mind as you go forward. Let me know if you have any other questions, and I will see you next time.
Thank you.
You're welcome.